Riddle me this, Mavaleka.
You roll a fair dice until you get a 6. What is the expected number of rolls including the roll of 6 conditioned on the event that all previous rolls were even numbers? This problem is difficult even for mathematicians. It was posted to a blog which generally covers graduate-level mathematics. Over 1,000 people guessed what the answer would be from a list of possible answer choices. Only about 18% got the correct answer. Furthermore, over 50% of this mathematically educated audience guessed the same wrong answer choice. The problem is quite counterintuitive. I also want to mention one more point that according to the Oxford English Dictionary, historically dice is the plural of die, but in modern standard English dice is both the singular and the plural. In this video I will be using dice as the singular. With that context in mind, can you figure out this problem? Give this puzzle a try, and when you're ready keep watching the video for the solution. Before I get to the solution, let me go over the answer. It is 3 halves or 1.5 rolls. Now the most common incorrect answer choice was 3 rolls. So why do people think 3 was the correct answer? When you roll a dice there are 6 possible outcomes. Out of these one of them is a 6. So the probability of getting 6 is 1/6, and you can calculate that the expected number of rolls to a 6 will be the reciprocal of that, which is 1/1/6 or 6. In other words, as the probability of rolling 6 is 1/6, we expect that it'll take 6 rolls to get a 6 on average. So what many people thought with this puzzle is that the probability of rolling a 6 when you have an even roll will be 1/3. There are 3 even numbers, 2, 4 and 6, and the probability of rolling a 6 given that it's even is 1 out of these 3 possibilities. So they used the logic that the expected number of rolls to a 6 given an even roll would be the reciprocal of this, which is 1/1/3, and that would be 3 rolls. But this is not the correct answer because the puzzle is asking for a slightly different question. It's asking for the expected number of rolls to 6 given that there are even rolls before the 6. This is a slightly different question. And I'm going to show you why the answer is 1.5. So when you roll a dice there are 6 possible outcomes. We need every single roll to be an even number, and the first roll could be a 2 for example. Then we roll the dice again and we have 6 possibilities, and we need this again to be an even number. So let's say it's a 4. When we roll the dice again there's 6 possibilities, and let's say we get a 6. Now the sequence will terminate. We have a 2, 4 and 6, and that's it. So we'll be considering sequences of this form. In other words, we're rolling even numbers which are 2s and 4s until we roll a 6. The sequence of rolls we will be considering will have the form E, so on until the roll of 6, and in this case E is equal to 2 or 4. But what's special about 6? Imagine we rolled until we got a 1. If we only had rolls of 2s and 4s until we got a 1, the sequence of rolls would be E all the way into 1, and notice the sequence length would have exactly the same distribution because rolling until a 6 is exactly the same as rolling until a 1 because 6 had 1 occur with the same probability. But then there's nothing special to the roll of 1. We could also do the same thing until we roll until at 3. If we have only 2s or 4s until a sequence terminates in that 3, this would have exactly the same distribution as the other sequences of rolling to a 1 or rolling to 6, and the same thing for rolling until we have the 5. So what does this mean is that we're looking at sequences where we have 2s or 4s until we roll any other number, which could be 1, 3, 5 or 6. So the question is, what's the expected rolls to X, or what's the expected length of this sequence, which I'll denote L. We can figure this out from a logical consideration. If we roll 1, 3, 5 or 6 in the very first row, that's 4 out of 6 possibilities, then the length of the sequence will be 1. But if we do not roll that means we rolled a 2 or a 4 in the first roll. In that case we wasted 1 roll, and then we still expect to roll just as many times until we end in a 1, 3, 5 or 6. This is a memoryless distribution. After we have wasted the first roll we're still going to expect a length of L to get our sequence to terminate. So this will be the second half of the expectation. So now we can substitute in the probabilities that the first roll is X, that'll be 4 out of 6 possibilities, and the probability of the first roll is not X, which will be 2 out of the 6 possibilities, which is 2 or 4. So we now have an equation for L. We can solve this equation for L and we'll end up getting that L is equal to 6 sports, which simplifies to be 3 halves or 1.5 brawls, and that's the correct answer. So if this explanation wasn't satisfactory I'm going to provide another way that you can get the answer. We can directly calculate the expectation using the definition of a conditional expectation. So let's calculate the expected number of rolls until a 6 given that there are only rolls of 2 and 4 before we roll to the 6. In this problem we can write the conditional expectation as follows. We have the expected rolls to 6 and we have only 2 or 4 rolls for the n-1 rolls until we get the 6, and we're going to divide this by the entire event where we only have 2 or 4 rolls until we get a 6 in some roll, either the first roll of a second roll, the third roll, and so on. So I'll first expand out the numerator into summation form, and now let's calculate the denominator. We need to know the probability that we get only 2s and 4s before we roll a 6 in some roll. This will be the sum from 1 to infinity of the probability that we roll 6 in roll k times the probability we only get 2s or 4s before roll k, which will be the rolls all the way up to k minus 1. Now the probability that we roll 6 in any particular roll will be 1/6, and then the probability that we roll only 2 and 4s up to that roll will be the probability 2/6, which simplifies to be 1/3. All the way for each of the k-1 rolls before we get the 6. So now how do we calculate this infinite series? We can write out several of the terms, and now we have a geometric sequence on the right. This starts with the term 1. It has a common ratio of 1/3. So we can calculate its sum by the formula A divided by the quantity 1 minus R. Substituting in those terms we get 1 divided by the quantity 1 minus 1/3, which will simplify and simplify again, and now we can figure out that the probability we only get 2 or 4 rolls before we roll a 6 is equal to 1/4. So this becomes the denominator, and now we're dividing by 1/4, which will mean that we're multiplying by 4. We now have to figure out this summation. But we've already calculated some of these probabilities. The probability that we roll a 6 on any particular roll is 1/6, and the probability that we get 2 or 4 up to that roll will again be the product of 1/3 to the power of n-1. So now let's factor out the 1/6 from the summation and write out some of the terms of this summation. So how do we figure out this sum? Well, it turns out this is kind of like a geometric series, but it's being multiplied by increasing terms, so it's known as an arithmetico-geometric series, and it is a common ratio of 1/3. So because the common ratio is between -1 and 1, it's a property of arithmetico-geometric series that it'll converge. So I'm going to tell you this sum converges, and now I'm going to show you how you can evaluate this sum S. It's going to be very similar to solving a geometric series. We'll multiply the entire summation by the common ratio of 1/3. If you look at what this will have been turned by term on the right hand side, we'll essentially shift over the summation one term to the right. We can now subtract the second equation from the first, and we'll cancel out all of these terms. So we have the sum times 2/3, which will be equal to essentially one term of each of these factors of 1/3 to the power of something. So what we've done is we've turned our arithmetico-geometric series into a standard geometric series. This has a common ratio of 1/3 and it starts with 1, so we can use the formula for the sum of a geometric series. We then simplify this formula and then simplify again, and then we end up with S times 2/3 is equal to 1, and now we take the reciprocal of 2/3, which ends up being 3 halves. So we figured out once again that this expectation is equal to 3 halves or 1.5 rolls. Did you figure out this counterintuitive puzzle?
Riddle me this, mother lecker.